Hello and welcome. In video part 1, we built a model that predicts fuel efficiency of a car given some details about the car. However, even though we built the model, we didn't go through details. So in this video, we're going to deep dive into the model and try to understand what the model does into details. So now, before we do that, let's just imagine what should we have done? What would you have done if this problem was about to predict the fuel efficiency, but without using machine learning? So in classic programming, or maybe let's say normal programming, you would build a function. In this case, I'm calling that function a program. And the function will expect to get some input, like parameters of the function, and then it will do some modification on the input or evaluate some conditions, and then it will output a number which says how many mpg or miles per gallon it thinks this is given that input. However, if you think about writing a program where you have to tell the machine all the exact details to follow to produce that number, that prediction, that would be a daunting job. So luckily with machine learning, you don't have to do that. So the way machine learning works is instead of telling the machine what to do, you actually want to provide some information, some examples, and then the machine will see a lot of examples in a way that it will understand a kind of relationship between the examples that you're providing and the output that is supposed to produce. So let's assume you provide to a machine details like these ones, where you have cylinders. In the cylinders column, you have, for example, the first example have 4 cylinders and then a weight of 2,790, an acceleration of 15.6, and then it will produce an mpg of 27. And then you give another example, and the third one, for example, 6 cylinders and then a weight of 3,415, acceleration of 15.8, and it produced an mpg of 22.4. So you keep providing these examples, lot of them, to the machine, and you hope that the machine will learn. But how does the machine actually do that? How does the machine look at these examples and learn how to produce the output, which is the mpg? So this is the theory how the machine does it. So the machine will get the input. So your machine learning model, but at this point, let's just call it our program. So it will take some input, and then there are going to be some transformation happening on the input, and those transformation will happen given the input and some weights, and that will produce an output. And we're going to have an evaluation mechanism which will evaluate the output and then update the weight. Okay, so how does it do that? In terms of machine learning, we'll have something like this. So we'll have the input, and then we'll have some sort of functions where the input gets passed through, and then the input is transformed using weights, and it output an output. And that output is passed to another mechanism called loss function, which will take the actual values, in this case we call labels, and then produce the difference. It will evaluate, given this generated output and the actual values, how far are they from each other. And then depending on what it found, it will inform another mechanism called optimizer, which will tell this is how good the prediction was, so can you please change the weight so that next time you will make even a good prediction. All right, so if we try to put this into the perspective of our problem, the input will be this information, and then this information will be passed, and the label will be the mpg. All right, so this information will be passed as input to the function. And then there's going to be some random weights which get applied to that input and produce an output. Now the real MPG will be compared to the predicted MPG via the loss function. And the loss function will take the real MPG, the predicted MPG and the real MPG and compare them to find how far are they from each other. Now, after finding that, it will pass that information. The whole function will be passed to the optimizer, and then the optimizer will use a mathematical formula of stochastic gradient to update the weight in a direction that will improve the next prediction by reducing the loss. So it will minimize the loss. So to get more details on how this is done, let's write the same model from scratch, where we'll be focusing into building these building blocks one by one and see how it works. All right, so let's do that. All right, so I've got here another Google Colab notebook that I'm going to use to show how we develop this regression from scratch. So one thing to notice is that I'm not going to be using a GPU during this notebook, so I haven't chosen GPU. And this is recommended every time you're not using GPU in your notebook. Make sure I don't choose GPU, because Google wants to spare these resources to other notebooks that are using GPU. So this will make easier for everyone else who's using the GPUs, as you won't be using a GPU. We won't be saving a GPU that you're not using. All right, so the first thing, I will download the FastAI library, and then I will after installing the FastAI, I will pull I will import all the libraries that I will need in this notebook. So the reason I installed the FastAI, despite that I'm going to do this thing from scratch, it's because I want to use this function here, this module download data, just to download this data. Okay, so let's start by getting our data. So we're going to get this data from the University of California website, and the data set has information about cars, and we want to use that information to predict the MPG, miles per gallon. And yeah, so we'll do that. We'll download by calling this function, pass it the URL, and then we're interested in only into this field. So we'll only download this field. We'll only pull this information and put them into a Panda data frame. So this is how you read a CSV into pandas. Okay, so now we print last five rows into our data frame, and you can see them, and this our beautiful data. Now after that, we still want to check if there is no missing values into this data set. By doing that, we can find that there is about 6 missing data into the column horsepower. So unlike what we've done with FastAI, which take care for us into at replacing this information, what we're going to do here, we're going to drop this information to make things easier. All right, so but this is in a normal project, this are just 6, but usually you will find in other data sets that have thousands of missing information, and you don't want just to drop rows because you're missing a particular column. So what you have to do, you have to come up with a strategy by looking to data and decide what kind of replacement you want to do. So the common ones could be replace the missing information with the mean of the information of the same kind, or it could also be means replaced with the median. Some other would replace by some number, let's say -1, which will just tell them this is every time I see this is missing, but usually that happens into when you're dealing with categorical data. And you others will use something like k nearest neighbors to predict what would have been the number if it was there. All right, so for us, we're going to drop this number, and then we remain with a data set now short of 6 rows. And the next thing to do after we've dropped these 6 rows, we want now to do the origin. So the origin was as you can see, it's a number 1, 2, and 3. 1 representing the USA, 2 Europe, and 3 Japan. So we want to replace this number with the actual country names, which is done here. But then, since we're going to build this by ourselves, we're not going to fit a model something like US or Japan, like a text. We're not going to fit a text. The model will always expect a numerical digit. They will expect something numerical. So what we're going to do, we need to do something called one-hot encoding, which is basically saying I'm going to expand the information that is in this row, in this column, and I'm going to expand into new columns. But then every time I have a car that was made in US, there's going to be a column called US, and we'll have 1. The remaining of other columns will have 0. So in this case, Europe, Japan will be 0, but the US will be 1. And you do that for all the data. If the car was made in Europe, only Europe will have 1, then Japan, US will have 0. That's one-hot encoding. So we've done that using get dummies from Panda, and this is the new look of our data set. All right, now if we check the shape, we'll see that now the new data set has 392 rows and 10 columns. Okay, so now the other thing we want to do is we've checked previously when we were building this with FastAI, we've checked the statistics, and we saw that these data are not on the same scale. So you can see, for instance, the weight has 2,720. All right, whereas when you see at the acceleration, it's only 19. So there is a lot of gap between these two. You don't want to fit your model with data that are this much different in terms of scale, because the calculation will be tilting towards those with big numbers. So what we want to do, use a technique called normalization, which will try to put this whole data into same scale, at least by having making sure that they're running and they have a same standard deviation. So here, to do that, we have this class called normalize. This is an extra data copied from FastAI. So what we'll do, we'll just take for every entry, for every column, it will evaluate what is the standard deviation for that column, what is the mean for that column, and then for every single row, it will take the value in the column that it's calculating minus the mean for that column divided by the standard deviation. But now, if the column has similar values, then it may happen that this column has a 0 standard deviation. To avoid a problem when dividing by 0, we just add a small number to make sure that the denominator will never be 0. So we'll add 0.000001. Okay, so, and then we want to normalize this data. And remember, when you normalize, you're normalizing only the numerical values, so, or otherwise the what we call continuous values, not categorical. So if you have things like categories like category 1, category 2, and category 3, you don't want to normalize that because those are just categories. But when it comes to so those will be categories, and they will be categorified by doing other ways, like calculating the as we've seen here, we've showed one hot encoding, but you can also treat categories using embeddings. So we'll see that in later videos, but for now we're interested in normalizing all numerical, all continuous values. Okay, so we've now normalized them. We've said normalize from this data set only continuous values, and as is now we see the new data set, we'll see that after normalizing, all the continuous values will have you can see that the standard deviation have changed now to 1. And indeed, if you look at the weight, you see that the weight is no longer between 1000 and 1000. It's now just minus 1.6, and the maximum being 2.5. So this is really a very good thing. Okay, so now after that, we want to create our features. So the features will be all these other columns, all this other information that we want to fit to the model, and this MPG will be our target or label. In this case, we want to get all the information related to the label under variable labels, and all the features under features, and we pass them to a tensor in PyTorch. Okay, and now after that, we can print an example of the first example and the first label to see how it looks like into Python tensors, PyTorch tensors, and this is how it looks like. And then we can also do the normal observation by building these graphs and printing these graphs and see if there is a relationship. So there is definitely relationship, as we've explained in the previously when we were building with FastAI. Okay, so now after we've seen all this, we want to import this data. So with FastAI, we had this tabular loader, which did the work for us, the heavy work of loading data to the model. But now this time, I want to show you how to do this from scratch. This is the function that's going to do it, the data etal, which will take a batch size. In this case, as I had said before, we would want to see only 64 examples at a time, and then we pass them to the model. So this batch size in this case will be 64, and this is our features and the labels, and we'll shuffle them. After shuffling them, we loop through our data set and pick only 64, a batch of 64, and return it and its corresponding labels. All right, so here we define our batch and pass it just for testing, and see indeed we can see what we get out. So after we've done that, we initialize our weight. Okay, so we want to initialize the weight in a way that there won't be very big gap between weights. So we want to initialize our weight by following a normal distribution with a mean of 0 and a standard deviation of 0.001. And how many weights we want to do. So for each information we enter here, for each column, I'm going a little bit back here. So remember, we said we have 9 features, these 9 features, and 1 label. Okay, sorry, these are 6 plus 3, so these are 9 features and 1 label. So what we're going to do, we're going to take this, we're going to create a weight for all the 9 features. All right, so this is where we do that. We say create this weight from a normal distribution with mean 0, standard deviation 0.001, and create 9 of them. All right, and since we'll be updating this one through the optimization, we want to tell PyTorch that this information will be updatable by assigning this requires grad true, and this is the way we tell PyTorch that this will be updated during the optimization. And we do the same thing for the bias, which is just one bias, because we have one, we're predicting one number at a time, so we're going also to have one bias. Okay, and then after that we define our model. So since with FastAI I've talked about layers, where we said we want a layer of 62 and another layer of 32 and another layer of 1 unit, which equal to the output. For simplicity here, we're not going to develop all those layers. We just want something normal, and that's why we're going to use a linear regression model. So the linear regression model will just be this way. We're going to take for each column and multiply it with its weight, and then we add another column multiplied by its weight. So we take each column multiplied by its weight, add them together and add the bias, and they generate the output. And that could be also presented in a neural network way by just showing this input layer where we have all these 1, 2, 3 up to D. So D in this case for us it's 9 columns, and all of them entering and being subject to the weight. This arrow shows the weight, and then they add together into producing the output. So let's do this in a code. We're going to do a torch matmul, which is matrix multiplication of between our input and the weight, and then we add the bias, and this will result in this picture that we have there. Okay, now that we've defined our model, this is the architecture of our model. We only have one layer, which is the output layer. We're now going to define a loss function. So the loss function, if you remember, maybe if I go back slightly into our slides, we've just built this func1. This func1 is, so the func1 is this function, linear regression. This is what we've just done. And then we're going to build, we're going to now to define this loss. We've created the weights, we've initialized them. We're now going to define the loss. We've already done the input, which was the function that was taking 64, which will be returning 64 input at the time. So now let's do the loss function. Okay, so the loss function is the next thing. So how do we evaluate the loss function? So the loss function will always take the input and the predicted value, and then we'll put them together to see how big is the difference. So in this case, we have our loss function. Okay, so loss function we want to use is called squared loss. So what the squared loss does is this. You have let's say this line, this is a line of prediction. This is your line that you created. Okay, your linear prediction, this one is producing this line. Okay, now these small the small blue cycles are the actual values, and now if you take the actual values and compare it to the predicted one, how far is it from the truth? Like how far is your prediction from the actual value? So the bars that you see there, they indicate the gap between the actual values and the predicted values. So what the squared loss will do, it will take all those bars, those gaps, add them. Okay, so the bars means the difference between the actual value, the predicted value, and the actual value. And then you take those values, you square them, and then you add them together. That's the squared loss. Okay, so the reason we square them is because we want to keep these numbers positive. So we'll add them, and then we add the sum of those squares. Okay, so so pretty much that's what we do, but we're adding here 1 and we're dividing by 2. So this is for the sake of making the loss calculation easier, because the loss, well, when we go to the optimization will do the gradient of this loss, which is taking partial derivatives of this loss. So if it's doing that, these two will cancel with the 2 into the denominator. So we just want to have that, it won't kill anything. Okay, so we defined our loss here. Now that we've defined our loss, the next thing is the optimization. All right, so maybe it's better if I go back here. So we can see the next thing is you have the loss, you now go to the optimizer. So let's define the optimization. All right, so our optimization now is a stochastic gradient descent. This is an algorithm that we're not going to learn right now, but we get time into other videos to talk about. We'll dedicate a video for stochastic gradient descent. But what it does in a nutshell is it's an optimization. It's a way of looking into that loss and try to update the weight into the direction that will improve. That will change the weight in a way when they apply next time to the input, they will produce a better approximation than the previous one. So to do that, it will do the partial derivative of the loss function with respect to the weights and the bias, and then every time when it finds the gradient, which is mathematically speaking means it's the direction of the steepest slope. So what it will do, it will just say, I want to minimize this function, so it will point into the negative direction of the gradient. And that's why when we create this stochastic gradient descent function, as you can see, we're looping through all our parameters, in this case W and B, and we're updating them by taking whatever parameter we had, and then we subtract with the gradient, okay, the average of the gradient, because we're calculating the gradient by batch size, so by batch, so we'll have to do the average of the gradient, and then we subtract that to the actual weight so that it points into the improvement direction, the direction that improves the weight and improve the prediction. But now we may want, there is something called a learning rate, which also we'll see when we talk about optimization. So the learning rate, what we'll do, it's just a number that you set up by yourself. It's not a magic number. It's just a number. You say it's like a step. You're moving into the direction that improve the prediction, but you want to define how fast can you move. Okay, so a big learning rate is just like you're taking a big step. A small learning rate is just saying, yeah, I want to go there, but yeah, I want maybe this terrain might be a bad one. I don't want to rush in and fall into somewhere, like there might be some gaps or pitfalls, so I don't want to fall. So what I would do, I'll just take small steps. Okay, so that's what the meaning of learning rate. And you always want to, after calculating the gradient, after updating the weight, you want to make sure the gradient object is set to zeros. The reason it's just you don't want to keep bigger number, you keep accumulating, and that could have bad impact. All right, so now we've got, if we look again to our map, we'll see that we've now finished the optimizer. We've initialized the weight already. The optimizer will be updating. The only thing now that we need to do is putting this whole thing together, which is building this model. Okay, so let's build the model. So this is how we're going to build the model. Each model, and this regardless whether we're using FastAI or anything else, we will always see this is the same thing. You have a loop. FastAI will abstract this loop. You won't see it, but the mechanism behind under the hood, it's the same. All right, so you have the learning rate. We've defined 003. We just want to move slowly. The number of epochs, so epochs will be how many times do you want to see each individual, how many times do you want to see each individual examples in your data set. All right, so because you're training by batch, you're taking a small batch, feeding to the model, The model does that linear regression thing, update the weights, return the output. Get again another example. So you want to, how many times do you want this model to go through the entire data set? So in this case, we said 20 times, so 20 epochs. And we've called our linear reg model and assigned to a variable called net. And we also called our squared loss function and assigned to a variable called loss. So we loop through our epochs and we call our data etal, which is this function which returns a batch of data. Okay, so we passed how many data size we want, features, and labels. Okay, so what we'll do, this will create batches, and then we loop through the batches every time, feeding the batch to the neural network, computing the loss, and after computing the loss, calling the gradient. Okay, so it's computing the loss, it's calculating the gradient. All right, so into our code, we're not calculating the gradient from scratch. We're just letting the PyTorch to take care of this for us. So we'll take the loss and do the sum of the loss so that we get one number, and then we pass this to PyTorch, which evaluate the gradient. And once we've got the gradient, we now call the stochastic gradient optimizer to update the parameters accordingly. Okay, so after that, after we've finished the complete epoch, every time after we've completed one epoch, we want to print out so that we can know if the model is improving. So the thing to print out will be, we want to print the epoch number, the loss of the training, but also we want to have the accuracy. We want, with the accuracy, we want to have a metric. In this case, it's not accuracy actually. We printing the square root of the loss. Okay, so we're doing mean square root error, which is our human way of understanding if the model is doing a good job in predicting. So since our metric, our evaluation metric is almost similar to our loss, there is no need to create a function for metrics on the side. So what I did here, I just took the metrics to be take the loss, but since we are dividing the loss by 2, I'm multiplying again with 2, and then what I do after that, I calculate the square root of that multiplication, the square root of the mean. Okay, and then I get the root mean square error of our model. So when we run this model, we'll see that it's actually indeed it's learning. It started from 174 and it went down to 7, and with our metrics for evaluation, the root mean square error showing 3.8. So this is mean we are approximating the MPG with plus or minus 3.8 error. All right, so let's say if the model, but that is the average. Okay, this is the average, but you would interpret like if this was 10, it's probably predicting 7. Okay, yeah, so we could get this down, but this is we just trained a few epochs and we don't have enough data, so this is what we can get from this data. Okay, and then after that we'll want again to see how far are we by looking at the prediction error, like is our prediction error centered into 0. So we built this histogram as we did before, and indeed we can see that it's closer to 0. And if we print the density of this histogram, we can see it's a bell-shaped curve and almost centered in 0. All right, okay, and as usual, let's just print and see how far these data are from the actual data. So this red will show the actual data, and this is how far we are, and we've got a bunch of data that falling inside the red line. So this is a good model. We now know each building block of this model, how it works. As you may have noticed, it's not easy to develop each building block from scratch, and it's prone to error. So in the next video, we'll go back to our previous implementation using FastAI and go line by line and show how in the implementation using FastAI library has fixed this issue for us by making the problem much easier to develop. So I hope you keep enjoying this series of regression model. And if you haven't subscribed, please do so, and hope to see you next time.